Hello, everyone. It's me again. I can still see some people are still coming in, so please help yourselves in, take your time. Actually, I was thinking maybe we can use this time while people are still coming to set everything, to make sure everything is doing well, especially with some announcements to be made for you to know. I know we've reminded you about this number of times by now, but it's very important that you make sure that you check ins and check outs, you do it at the same and right time. Other than that, my colleague Ali has mentioned yesterday about the tour to Al Balad. So in case you're interested to go to Al Balad during the weekend, make sure you register for that. Probably you've already received some push-in notifications already for that. Other than that, I think we'll just give it a few minutes till we have everyone in so we can start. Thank you.
Please be seated. The event is about to begin.
يرجى منكم التكرم بالجلوس. سيبدأ الحدث بعد قليل.
All right, so this evening we will have our first keynote, and the moderator for this session is again Professor Michael Berman, who at this point probably doesn't need much of introduction. We know he's the chair of this year's WEP, and he's a professor of marine science here at KAUST, and as we learned yesterday, he is a fan of Jigsaw. And it seems like every day we're going to discover something new about him. So here's today's fun fact to add to the list. So he was once a scuba diving instructor. No surprise, he ended up as a marine scientist after all. And with that, please allow me to welcome again to the stage. Thank you.
Thank you. Welcome to this evening's session. And it's a pleasure to introduce our keynote speaker for tonight. Professor Sam Purkis is a longtime friend of KAUST and longtime friend to Saudi, has had a lot of experience in the Red Sea, which he's going to tell you more about. Sam is originally from London in the UK. He's been in Miami in the US for about 20 years now. He's currently a professor at the University of Miami, and he's also the chair of their geology department. Sam has had a lot of different roles in leadership in science. He is the chief scientist for the Living Oceans Foundation. He's had a lot of experience on many different vessels. He's led cruises with Ocean X Foundation. I think we'll see some of that as well. And it all started due to a chance encounter with a person on a beach that he's going to tell you more about, so I don't want to steal that story. He has his PhD from the University of Amsterdam, and he is collaborating with a lot of different people here at KAUST, and he most recently was here as a keynote speaker for a marine conference that we had about 1.5 years ago. So I'm really excited that Sam is able to come and talk about the outliers that he's familiar with, and in particular tell you maybe some things you did not know about Arabia and the history of Arabia, highly relevant for where Saudi thinks it's going now. A couple of fun facts to share about Sam. He is the proud father of a few chickens, And they're really amazing. If you're ever in Miami, I'm sure he'd love to introduce you to the chickens. He is also a motorbiker and has quite some adventures motorcycling that I think would make for a great talk another time. But tonight we're going to hear about Arabia, so let's please welcome Sam for his keynote talk tonight. Thank you very much.
Thank you. Okay, thank you so very much, Mike, for that introduction, and thanks to the entire organizing committee of this WEP. I mean, it really has been a seamless and fantastic experience from the moment that I landed in the kingdom. And it was Mike who initially extended that invitation to me, which I, of course, gratefully replied to. I am a long-time friend of KAUST. I've been here several times, going back to when it was opened. And, of course, I was eager to jump on a plane and come here and give this seminar. And for that invitation, what you're going to get is the following. I'm going to talk about this outlier technology that myself and collaborators at KAUST, and I'll be introducing them to you as I go through the presentation, had the opportunity to work with OceanX, this incredible organization and their research vessel I'm going to show you about momentarily. And that work was funded by NEOM up in the northern part of the Red Sea and going up into the Gulf of Aqaba. And we made a discovery in the deepest part of the Gulf of Aqaba, which tells us about outlier conditions in the ocean. This is some of life at its most extreme on the planet. These are hypersaline, brine-filled lakes that we find at the bottom of the sea, inhabited by microbes which exist under that extreme pressure and extreme chemical environment. And those discoveries really help us when we start to think about life elsewhere in our solar system and beyond, how extreme life can be on this planet. And I'm going to show you, once we discovered those brine pools at extreme depth, how we learn about outlier climate events which have happened in northern Arabia going right back to Roman times. And I'm going to be particularly talking about how rainfall has changed radically in the mountains around us in the last 2,000 years. And then I'm going to wrap up with some key findings which I hope bring winter enrichment to all of us. All right then, so I'm coming to you from Miami. This is the Rosenstiel School. You can see downtown Miami in the background there. And please come and visit me. Anytime you're in the region, come to Miami, come to the Rosenstiel School, and I'll tell you about the work we're doing beneath and above the waves. But I'll tell you one thing, we'll be ashamed by the facilities we have in Miami compared to what you have here at KAUST. I mean, it really is an outlier institution, and I hope you're enjoying your time here, because I can tell you, if you go to another university, it's just not like KAUST. This is something really very special. Now, all of the work I'm going to present is a team effort. I really want to thank my postdocs, Bolton, Akosh, Jake Morgan, Arash, he's a research scientist, Professor Amy Clement, a climatologist. I've been working with Ben Randall at the University of Potsdam. But my main thanks are reserved for two individuals. I want to thank Francesca Benzoni and her entire team in the Habibi lab here, and Mike Berriman and his Reef Ecology lab. Those collaborations and the teams that they run are truly one of the highlights of my professional career, and I say that most sincerely. I want to thank too Christopher Clark. He's from the Desert Research Center here. OceanX, of course, who facilitated all of this work, and NEOM, who funded a great deal of it as well. All right, on the topic of team efforts, I do want to give sincere congratulations to the Kingdom for recruiting Ronaldo. I mean, that was really a coup, wasn't it, to Al Nassr Football Club? And the only way you could make that situation better would be to pair him with Lionel Messi, wouldn't it? And I know you tried. The Kingdom tried to get him, but no, he came to Miami. What a great place, you know? So I think we'll take it as a 1-1 draw for our respective base camps when it comes to soccer stars. And my final thanks is actually going to be reserved for the Ottomans. Great group of people ruling through the 16th century, northern Arabia, and they kept absolutely excellent records about the climate in the region that I'm going to be referring back to. And I think it would be remiss not to also thank the Ottomans for the couches. I mean, those are the most comfortable couches that you can imagine. So a great thanks to the Ottomans, and we'll be coming back to those as we work our way through. Now, the Red Sea is a truly fantastic place to work. Geologically, we have two plates moving apart. The Arabian plate is moving from the African plate and literally tearing a hole in the continent, making this young marine basin. It's also interesting for humanity. This area, bounded to the east by the Tigris and the Euphrates, and the other side by the Jordan and the Nile, is one of the cradles of civilization. It's here that we see the invention of first agriculture, irrigation, writing, the wheel, glass, and so on, but also waves of early hominids coming out of the Rift Valley in Africa, starting their migration around the world and coming through the Red Sea region. Now, as a geologist, this is a fascinating place to work because it shows us how ocean basins are born. If you were to come to the North Atlantic Ocean 170 million years ago, you would see a situation very similar to the modern-day Red Sea, about the similar in the length, the breadth, similar displacement from the equator, even the climate is the same. So as a geologist, we come to the Red Sea to understand how oceans are born. And I've been coming here for a really long time. That's me in the foreground. I started work in the Red Sea in the early 90s, which seems like a really long time ago now, if I'm honest. I'm there with my dog, and I was living in a tent in southern Egypt, teaching scuba diving, and I just fell in love with this part of the world. I think it's that arid, hostile climate that you have in the desert, and then you just step across the coastline and you see some of the most luxuriant, vibrant coral reefs that the planet has to offer. That contrast is so stark and so amazing. And I was living in Egypt. It was truly an outlier experience, and I just had a chance encounter with an outlier individual. I was going to art college at the time, studying fine arts, and I met someone on the beach there, a geologist, Jeroen Kenter, who totally changed the perspective of what I wanted to do with my career. So I quit art college. I then went to do a bachelor's degree in the UK in marine biology and oceanography. I moved to the Netherlands. I did my master's and PhD, and then came across to the United States, where I've been for the last 20 years, and worked my way up from postdoc up to a professor. And that was one of those sort of outlier encounters that really changed or plotted at least the chart of my career. Now, a second opportunity, if I was going to draw a second node in that arc that I've traveled, it's much more recent. In the last 5 years, we had this incredible opportunity to work with OceanX. And by we, I mean myself and also collaborators here at KAUST. And the reason this is an outlier opportunity is because they have this incredible research vessel, the Ocean Explorer. I mean, it really is something beyond compare. And we took 3 cruises in 2020, 22, and 2023, working all the way up and down the northern Red Sea and up into the Gulf of Aqaba. And what an incredible vessel this is. I mean, as a marine scientist, it just blows your mind. Of course, it's got a helicopter. I mean, why wouldn't it? I mean, everyone needs one of those. And then beneath the water, on your left here, there is 2 deep diving submersibles. They each carry 3 people, a pilot and a couple of scientists, so 2 of those. And then on the other side there, on the right-hand side, that's the remotely operated vehicle. The ROV, we call that, which goes to much deeper water. So the submarine, we can go down to about 1,000 meters, and the ROV down to 6,000 meters. And that robot is tethered to the vessel above using an umbilical. I mean, it's truly incredible what you can do with such equipment. And we just had great fun. I mean, we were doing good science, learning so much about this unexplored area, spending tens, hundreds of hours in the submersibles, really learning about what goes on in the northern Red Sea. And it's not just those assets that make this an outlier technology, it's also the capability of the ship to map the seafloor. So we do the dives in the submersibles during the day and go to bed, and then at night, the ship is now mapping the water depth, making these sort of maps. The different colors here represent the different depths of water. And then as a scientist, we get up early, sort of 5:30 in the morning, quick cup of coffee, and then down into mission control of this huge vessel, and you start to see the data which have come in from the night before. And in many places in this region, the seafloor has never been mapped previously, and you are the first people to see what's going on. In this case, these drowned reef pinnacles, which are being translated and rotated by huge underlying geological forces. And it's one thing getting up in the morning and seeing that data set, it's a whole nother thing then being able to get in the submersible and go down 1,000 meters and actually look out and see those processes ongoing with your own eyes. It's an absolutely incredible experience. Now, one discovery that really stands out, at least for me on that expedition, was this work we were doing in the Gulf of Aqaba, where we found these underwater brine-filled lakes at more than 1 mile water depth. So we're really, really here in the deep water. And they became known as neon brine pools. We're too deep here for the submersibles, unfortunately. So this is all done using the robot submarine, the ROV. And you can see over there, they even let me drive it, which was probably a huge mistake. And we're working in the Gulf of Aqaba. And you see the blue area there is a point where it gets particularly deep, more than 2,000 meters water depth. And we had done the mapping, and you can see on the other side there a zoom in. And I was looking at that map. It was particularly deep, the water, and you have this network of geological faults. And I just had a hunch that maybe this is the sort of situation where you'd find these underwater brine lakes. And the reason for that is we might have seawater which is mobilized through the geological faults down beneath the seafloor. And the peculiar thing about the Red Sea is buried in the subsurface is huge quantities of salt. And that has to do with the geological evolution of the Red Sea. I don't have time to go into that, but you have Professor Abu Dafifi here and Dr. Tihana Pensa, who just defended her PhD. I mean, we have experts at KAUST who really understand this in huge detail. Anyway, my hunch, I thought the seawater could be working its way down, interacting with this salt, forming a brine, and then through hydrothermal processes being mobilized back up to form these brine-filled lakes on the seafloor. That was my hunch. Now, as you might imagine, this vessel is incredibly expensive. To have 1 day of research on that vessel is absolutely eye-watering. And if we're going to go looking for the brine pools in the deep water, all the other scientists have to stop their work, because there's no way we can launch the submarines and so on and so forth. We're solely focused on now searching for brine pools. So I negotiated with my colleagues, the chief scientist, and it's okay, Sam, you can have 1 day, but you better find the pools. So in we go, early in the morning, down to 2,000 meters water depth. It takes about 2 hours to get down there with the robot submarine. And what we encounter is this barren, featureless, muddy seafloor. I would say boring. Nothing's boring in the deep sea. Let's say this is boring adjacent. But, of course, we weren't expecting to find the pools immediately. That would be, life is just not that kind, is it? So we started our transect across the deep, muddy seafloor. And 1 or 2 hours, the first joke started to come, like, Sam, hey, where are the brine pools? Well, I said, don't you worry about that, my friends. They're just around the corner. And then 3 hours, and then 4 hours, and 5, 6, 7, and nearly 8 hours, and nothing but mud. Goodness, I thought I had written a check that I couldn't cash. I thought the whole thing was a complete bust. And I was ready, I was so despondent to say, okay, let's quit, let's pull up the ROV and write the day off to experience, and I'll spend the next days keeping a low profile, having wasted everyone's time. But then, literally in the last 2 minutes of this dive, the first brine pool came into view. And it's absolutely beautiful. Remember here, we're at 1 mile water depth, and we have this underwater hypersaline lake filling a depression on the seafloor. It's small but perfectly formed, and the colors around the edge of the pool are these extremophile microbes which live in that hypersaline brine-filled environment. So a beautiful tiny pool, and then we lifted up the ROV and flew over the top of it, and then came down behind it and found an absolutely huge brine pool, more than 10,000 square meters in area, like absolutely fantastic. And you see here, just coming into view. And you notice as the thrusters on the submarine push down on the brine, we get like this slow motion wave because the brine is so dense, everything moves really very slowly. once we've made the discovery, of course, I feel that I've been let off the hook, we can lower down sensor packages from the vessel, and let me remind you, that's 1 mile above, and start to sample this incredible environment. And you see the brine here spilling off the side of the framework of that scientific equipment as we pull it back up to the surface. And what we find is the brine is completely devoid of oxygen. Any animal that goes into the brine is asphyxiated and killed immediately. And that gives an opportunity for these predators like the shrimp, which are actually quite big, much bigger than you'd think, which use this as a trap. So they swoop in complete darkness and scoop any dead animal that's been asphyxiated in the brine and prey upon it. So this is an incredibly biodiverse point on the seafloor at incredible depth, in stark contrast to the otherwise sort of bleak and depauperate muddy seafloor which stretches for tens and hundreds of kilometers around the area. Okay, so that was the discovery of the neon brine pool. Certainly one of the highlights of my career so far. We've managed to return, having made the discovery. We can actually fit a mapping package onto the robot submarine and now map it in exquisite detail. We're working on the microbes which inhabit the brine and their unique genetic signatures and their interaction with giant viruses which live in the area. We've mapped out the small pool, our initial discovery, and now start to understand how the brine is coming out of the seafloor. We know exactly where those springs are because the seafloor is stained by the microbes which are living within the brine. And these are not unique discoveries in the Red Sea. There's been brine pools discovered before, not in the Gulf of Aqaba, so that was something new. But what makes this pool so incredibly special is its proximity to the coastline. Even though we're in 2,000 meters water depth, we're only 2 kilometers away from the coast. And what that means is that if anything happens in the desert through history, for instance, if you have strong rain events, sediment is washed out of the mountains through the canyons, you call them wadis here, through the canyons, down submarine canyons, into the brine pool waiting 2,000 meters below. And because the brine pool has no oxygen at all, that record is exquisitely preserved. On any other part of the seafloor, which is oxygenated, you have a myriad of organisms chewing their way through the seabed, searching for food, and we call that bioturbation. And those are worms and mollusks and shrimp and so on and so forth, constantly chewing through the seafloor, but not in the brine pool because there's no oxygen. So it has a unique record of what's been going on in the desert in the last centuries and millennia. Okay, so I've been working with a colleague of mine, Ben Rendell. He's at the University of Potsdam to really understand the plumbing of the desert. That is, when it rains, how material is washed out of the mountains, down submarine canyons, to eventually be archived in the pool. And to get at that archive, we really need the help of OceanX and these outlier technologies. So here we go down into the deep again. So this is just the power of such a research vessel. What I'm showing you here is a picture. We're at 1 mile water depth, and we have an autonomous camera which we've situated on the coastline of the brine pool. We're then filming ourselves, that is the robot submarine, coming down, and we're going to land it on the surface of the brine. That machine weighs about 10,000 pounds and is the size of a small truck, and we have to delicately choreograph the landing in the brine. And then we can start to use the manipulator arm here from the ROV, and we're pushing these cores down through the bed of the brine pool, retrieving the sedimentary record, which is archived beneath. So there's one of those cores going in. We're just giving it a little tap there. You can see the sediment entrained under the brine surface, and we pull that up. We stow it on the front of the ROV and then hoist it all the way up to the surface. In subsequent years, we came back with a little bit heavier duty equipment. This is what we call a gravity corer, which is essentially a huge lawn dart that we can drop from the ship, and it gains huge velocity, and we can stick it through the bottom of the brine pool, and that's another way of getting a little bit further back in time. So those cores are frozen. They made their way back to Miami, and then comes the day where we have to open them. So we defrost them and we open them up and start to read the record, just like reading the pages of a book. So there's one of the cores. You see beautiful layering and colors. The top of the core represents the modern-day seafloor, and as we go down it, we're going farther back in time. So the bottom of the core in this case corresponds, as I said, to about the fall of the Roman Empire. That's how much information we have locked in there. And there's really sort of two types of layering that really jump out at you. The first you see in the middle here are these dense sort of layers, lenses of sand, which we now understand represent huge earthquakes which have happened in the last centuries in the Gulf of Aqaba, and then, more frightening, the tsunami that those earthquakes have issued. And we've come to understand there's really a very substantial tsunami risk in the northern Red Sea and the Gulf of Aqaba. That's not the topic of this presentation, although I would love to talk more about it. In this presentation, I want to focus on these delicate layers that we see in the core, just a few millimeters thick, each one of them. And we understand exactly what those are because of work by Timur Katz and Bev Goodman further up in the Gulf of Aqaba, where they have filmed the mechanism that creates those layers in real time. And what it is flash floods. It rains in the desert, we mobilize water down through the wadi networks in the mountains, it picks up mud, and we get this plume of sediment that goes into the Gulf of Aqaba and then gently starts to settle down into the deep sea floor and form one individual flood layer documenting that this event happened in history. Rumor has it the diver is still down in the plume. So now we understand that the cores have a record of rainfall in the region, and we have all sorts of chemical and computational techniques to extract that record. I'm showing here one of the tsunami deposits. Happened about 500 years ago in the Neom area, but we're going to focus on the flood record, and we x-ray the cores. We use a technique called carbon dating to work out the age model, and here we have a record of rainfall which goes back over 1,600 years, and that's what I want to focus on for the rest of the presentation. Now, to understand what the brine pool is truly recording, we really have to understand how the desert is plumbed into the Gulf of Aqaba. And we start the journey of understanding for that using computer simulation. And this is with my friend and colleague Steve Ward in UC Santa Cruz. And what I'm going to show you here is a rain event. So there comes the rain. We see the wadi networks activate, and then we can track in the computer the plume of sediment which is delivered into the Gulf of Aqaba and settles down into the brine pool, which is the red dot there. Now, that might not seem very impressive as a visual for a computer simulation, but I tell you, if you see one of these flood events with your own eyes, it's a truly terrifying and fantastic experience. So this is after 40 millimeters of rain up in the Neom area of the Gulf of Aqaba. 40 millimeters of rain, we have that for breakfast in Miami. It's like absolutely nothing. But when it rains in the desert, you get these catastrophic, violent flash floods, and you see this huge torrent of mud-laden water screaming down the canyon and into the Gulf of Aqaba. I think it emphasizes two things. First of all, a little bit of rain in the desert can cause a lot of chaos. And the second thing is you do not want to be stuck in one of these canyons when it's raining in the desert. It's an incredibly dangerous situation. And we can track what happens after these events using satellites, and I show in the top right there, we can track the plume going into the Gulf and then starting its journey down to the seafloor. Now, I'm a coral reef biologist, or I was a coral reef biologist. I mean, that's what really interested me. But since working on this project about the floods, I've become really enamored with this topic. I mean, they are absolutely terrifying events. And this is two examples from Jeddah in 2022. Parts of Jeddah are built within the Wadi network very unwisely. You have a little bit of rain and an absolute catastrophe occurs. Of course, huge damage to infrastructure, but also very many lives are lost. I mean, these are very dangerous situations, and they seem to be becoming more frequent. Just last year, I'm showing here a similar flood in Oman. I mean, just a little bit of rain and utter chaos. And on the right-hand side here, in April last year, the entire airport floods due to rainfall. There's a lot of wind, terrible storms coming through Dubai. There goes someone's ottoman over the balcony. You know, I mean, they're great couches, but they're not heavy. That's the problem. So utter chaos when it rains in the desert. And the question now is, what can we learn about these events by looking into the past? How can the past inform the future? Okay, so what I'm going to do now is we're going to take that record that we took from the brine pools right down in the deep sea and project it to try to understand what's been going on in the desert over the last 2,000 years in this region. And I've x-rayed the cores here, flipped them on their side. At the top right is the present day, 2024, and the record extends all the way back to 500 AD, about the collapse of the Roman Empire in this region. And then the vertical lines represent these flood layers. We've had more than 150 of them occurring over the last 1,600 years. And we can look at the number of floods. The present-day average, in the last 100 years, there's been about 5 flash flood events, not very many at all. If you go back 200 years earlier, we have twice as many. You go back 400 years earlier, you have 5 times as many, and then it's oscillated through time between periods where these mountains have been very dry to much, much wetter than today. If you're getting twice, let alone 5 times as much rain, you could imagine the hyper-arid desert today to be green and a much more like savanna-like conditions, totally foreign to what we see in the modern era. Now, the problem with the brine pool is it only records the outlier events. That if you have a little bit of rain in the desert, thank goodness, it just soaks into the desert and doesn't cause you any trouble. But there's a critical threshold that if you surpass it, all hell breaks loose. And we have to understand what that threshold in rainfall is to understand what the brine pool is actually recording in the deep sea. How many millimeters of rain does it take to generate a chaos? Well, we get at that in the modern era using satellites. We can map rainfall around the globe now at 15-minute intervals, and particularly in this area that feeds our brine pool. It's about 300 square kilometers of mountainous desert. And we can use the satellite, and we can look back in the last 20 years, and there's been about 1,500 rain events. And how large those events are dictated by the size of the blue bar in my chart. And you can see most of the rain events are tiny, just a few millimeters, not going to bother anyone. But then we have those larger ones, 10, 20, 30, 40, 50 millimeters, which are potentially very, very dangerous. We need to know which one of those rain events caused the flash flood. To get at that, we use another satellite technology. It's called a Sentinel-1. It looks in the microwave spectrum at the planet's surface, and we keep an eye on this coastal road which winds its way up the Saudi Arabian Red Sea, and when we get to the Gulf of Aqaba, weaves its way between the mountains and the Gulf. And I think you'll appreciate from that drone image, if you're going to have a flash flood, it has to cross that road. So if we keep an eye on the road for every one of those rain events, we can work out how much rain is a flood trigger. And this is an incredible technology for 2 reasons. First of all, microwave remote sensing works day or night, and these floods can equally happen at night as they do during the day. But the second and most important is that the technology sees through clouds. Because, of course, the sky is full of clouds when we have these critical rain events, and we can look through the clouds and see what's going on the desert surface below. So we take images before each rain event and after and see if anything changed. Here we have an event from 2015, 26 millimeters of rain, not very much, and nothing changes. So everything, that seems to be beneath the threshold that we need to understand. Then in 2018, we have the 41 millimeters of rain, massive change in the reflectivity of the desert. Clearly, we've triggered a flash flood, and that's corroborated by our eyewitnesses on the ground. I mean, this was that terrifying event that happened in 2018. So it seems that 41 millimeters is above the threshold. We then go back to the computer simulation, and we settle that 35 millimeters of rain is the danger zone in the mountains up in the Gulf of Aqaba. If you have 35 millimeters of rain, it's enough to trigger a flood. You're going to move about 1 million cubic meters of sediment into the Gulf of Aqaba. That's going to spread out in a plume covering 30 square kilometers, and you're going to get a layer of mud deposited in the deep sea just 1 millimeter thick. So that is what our pool is recording. All right, now we have to do a little bit of math, and I don't want to go into too much detail, but what we can do is we can transform the thickness of the layers, therefore, as they're recorded in the core, to actual millimeters of rainfall, thereby making the brine pool a rain gauge, not over 10 years, but over 2,000 years. And what we see if we look at the frequency of rainfall in the region is that small events are very common. You often get a little bit of rain here, and the large events are much rarer, thank goodness. But there's a nice, what we call power law, fractal relationship, which relates the frequency of small to large rain events. So that's predictable. Then, if we look at the thickness distribution of our layers, they follow a very similar mathematical distribution. And then we can transform our layer thickness into millimeters of rain. There's 4 ways to do that, I think, and we've sort of got into the mathematics, but I want to look at the results. So now we have a rainfall record stretching back 1,600 years. And that's incredible. So we'll start over on my side here. At the fall of the Roman Empire, it seems the region is really rather arid, probably a climate which is similar to today. Then we start to see the rise of Islam in the region, and that's a comparatively wet period, much, much more rainfall than today. And as we go into the caliphate phase in the kingdom, it's getting wetter. Then we go back into a tribal social structure in the kingdom, and it's actually very dry again. And then the Ottomans come on the scene, and this all becomes part of the Ottoman Empire, and it starts to get very wet indeed. And you can see as we go up towards 1500 AD, we're at peak rainfall. That's going to be a very, very different landscape. As I say, it's going to look like a savanna, totally different to experience it today. And even 200 years ago, it's raining twice as much. It would have been a very different kingdom to live in at that time. So it seems that in the recent past, it's been much, much wetter. And we have people in antiquity moving through this region, which corroborates what we find in our deep sea record. And I'm going to take you, first of all, back 500 years before our core record even begins, and we'll look at the writings of Agathides of Cnidus. He's from ancient Greece. Cnidus is in modern-day Turkey, and he's working his way through the mountains here in the Gulf of Aqaba, actually looking at gold mining, which is ongoing in the region, and documenting what he sees. And he reports abundant lions, leopards, and wolves in these mountains, and lotus as tall as a man. Now, lions are fascinating for 2 reasons. Well, first of all, they're freaking dangerous. I mean, don't spend too much time around a lion. But secondly, they live within a very constrained amount of rainfall because they feed on large herbivores, which in turn require vegetation, which in turn requires a lot of rainfall. So for lions to exist in these mountains, you have to have at least 300 millimeters of rain a year, perhaps 1,500. So 2,000 years ago, it seems you must have 10 times the amount of rainfall as we do today. Then we start to get the early Arab geographers and explorers coming through the region, and we have Abu Abdallah here, and he's coming through in 1516 AD, which our course would advocate is one of the wettest periods in the record. And Abdullah, he reports springs of running water and abundant wetlands reeds in the Wadi networks that we see today, corroborating what we see in the deep sea records. And then coming forward in time, now to the European explorers, Rupel, he's coming through in 1826 AD, approaching the town of Al-Bad. It's about 40 kilometers inland from the coast, and he says that although no rainfall fell in several months, so we would think he's there in the summer, he encounters huge quantities of standing water, ephemeral lakes which are a foot deep and 50 strides wide, and the banks of the wadis are covered in thick bushes and abundant date palms where there's no such vegetation today. So clearly also advocating for a wet antiquity. And then finally here, we have Captain Burton in 1877 AD, who's trying to make his way across the coastal plain, and he encounters terrain which is too marshy for the camels to pass. So clearly very wet conditions as well. And I must say, Captain Burton, I think he has more than a passing resemblance to the late, great Freddie Mercury from the band Queen. I'm sure they're not related, but they certainly have a certain similarity. Okay, so antiquity seems to have been much wetter. Why is the desert so different if we go back even just 200 years, let alone 2,000 years? Well, it actually has to do with the amount of sunlight which reaches the Earth's surface. There's a strong understanding now, and we call that irradiance, that the sunlight reaching the Earth's surface controls the climate setup in northern Arabia. And we understand this irradiance curve very well because we can look at isotopes, we call them, preserved in ancient trees, and at least back 1,500 years, we know that the sunlight reaching the planet was actually considerably higher, say in 800 AD, and as we work our way forward, and I'm looking at the orange line now, we reach what we call a solar minimum around 1500 AD, and since that time, the amount of sunlight instant on the Earth has gone slightly up again. And there's two major controls of that parameter. The first is the activity of the star itself. Sunspots. The more sunspots you have, the more irradiance the sun emits. And the second thing is actually volcanic eruptions. It doesn't matter where on the globe the volcano is, it puts sulfur aerosols up into the high stratosphere, and that reflects solar irradiation, decreasing the amount of light which reaches the surface of the planet. And it's at this time when we reach that solar minimum that we're at the height of the Ottoman Empire. Up until that stage, that empire has been strong and considerably expanding year on year. And then we get into the 1590s, and the Ottoman Empire has an absolute calamity. There's a series of cold and wet winters which stretch across the region, inducing a famine which kills hundreds of thousands, if not millions, of rural Ottomans at that time, and then seeding the Salali Rebellion. This is the first sort of crack in the empire which has been so strong up until that point, which will eventually then collapse after the First World War. And then in 1621, there's many chronicles that tell us that the Bosphorus entirely freezes over with sea ice. So cold was the winter. I don't know if you've been to Istanbul in the winter. You might want to bring a jacket, but you don't expect to be able to walk from Asia to Europe across a floating pack of sea ice. I mean, it's totally unheard of in the modern era, but nearly collapses the Ottoman Empire. Now, I can show you statistically that relationship between irradiance and rainfall. I don't want to go into too much detail. The take-home message is that the changes in the sunlight reaching the Earth's surface are absolutely minuscule. We're looking at an annual change in difference of 0.05%. That would cool the planet by 0.07 of a degree Celsius, totally imperceptible. You wouldn't feel it. But in northern Arabia, that's enough to up the amount of rainfall by a factor of 5 and nearly destroy the Ottoman Empire. So there's this very delicate balance between what's going on with the sun, with the climate in Arabia. And the question is, why is that balance so nuanced and so delicate? And it all has to do actually with the jet stream. So I work with my colleague, Professor Amy Clement at the University of Miami, who studies such things, and typically the jet stream passes across the Atlantic in an east to west direction. This is all part of what we call the North Atlantic Oscillation. That's the typical position, but sometimes we get a blocking in the middle Atlantic, and the jet stream in the atmosphere diverts up to Greenland and then comes across Western Europe, now in a north to south direction, bringing intense rainfall into northern Arabia. And I can actually show you that with data. I'm going to map the rainfall over the last 20 years. And what you can see here, the blue is where it's raining. In January, February, March, April, the rain is pushing down into northern Arabia, and that's the risky time. Then we get into the summer months, June, July, and August, and that rain belt is going to migrate up to higher latitudes, up over the Mediterranean and up over the Black Sea. But once we get into the fall and back into the winter, you're going to see that rain belt starting to push back down across the Mediterranean into northern Arabia. And if you track the position of the jet stream, you can see that it very well predicts where the rain is going to occur. And so it seems that the position of the jet stream above us here is critical to understanding when, and how it's going to rain. And likely in the Ottoman times, we were in this negative phase of the North Atlantic Oscillation more frequently. Okay, then. So to wrap up here, what I've shown you is you could have a tiny change in how much sunlight is reaching the planet's surface can have a massive input into the amount of rainfall here in northern Arabia. You change the amount of sunlight by 0.05%, you increase the amount of rainfall by a factor of 5, and you kill hundreds of thousands, if not millions, of Ottomans and nearly collapse the Ottoman Empire. That's the start of the degradation of that great civilization, which finishes after the end of the First World War and gives the modern nation states of the Middle East, such as Iraq, Jordan, Syria, Lebanon, and Israel, and so on and so forth. It's all climate related. This has some real societal implications. What we see from the models that we're running in Miami now is that with warming climate, it's likely that you're going to have more outlier rain events in northern Arabia. These are not caused by volcanic eruptions anymore. These are caused by industrial aerosols being released primarily from Western Europe, which is changing the irradiance curve in the region. And this change can be subtle but catastrophic. Let's just take the example of Storm Daniel. That's a Mediterranean cyclone that comes into Libya in 2023. We get 2 to 3 times the amount of annual rainfall dropped in a single day. And that's how this happens. These are outlier events. That's a problem with rainfall in the desert. It's unpredictable and it's extreme. In that case, floodwaters wipe out entire neighborhoods in the port city of Derna, which is at the end of a long wadi, and estimates vary, but perhaps 10% of the city's population drown in a huge humanitarian disaster, just caused by one of these outlier rain events that we have to be aware of. Now, up in the mountains of Neom in antiquity, it really didn't matter if you had 5 floods per century, or 25 or 50. I mean, you might have inconvenienced a few lions, but there was no one really living there at the time. It's so rugged and inhospitable and remote. But that situation is changing radically. Now, with the giga projects in the kingdom, the desert is starting to be urbanized at an eye-watering rate. And it's these canyons that come down from the mountains, which are particularly beautiful. Those are the development targets, and then the beautiful embayments that we get at the heads of those canyons are where the marinas are being developed because it's beautiful and sheltered. Now, I don't want to be the guy to say that you can't develop in the desert because you're going to get washed away by a flash flood. I'm sure you can engineer around these sort of events. But what we've learned through this presentation is that if you look at the modern climate, it is the exception, it's not the rule. You only have to go back 200 years, and you are in a totally different climate system, and 400 years, it's unrecognizable. And if you want to speak to one group of people who occupy this region who can tell you what a tiny change in the amount of sunlight reaching the Earth's surface can have, just speak to the Ottomans. There's an imperceptible change in the climate, there's 5 times as much rainfall, and it nearly collapses the Ottoman Empire. So beware of those outlier climate events, particularly in this region. And I'm going to leave it there, but I do want to give a final thank you to the entire organizing committee for asking me to come here, and I'm happy, of course, to answer any questions that you have.
Thank you for an awesome talk. I really hope that it's inspired you guys to think of some tough, innovative questions for Sam. So please, there are microphones here. If you have a question, don't be shy. Stand up. Anyone? Who's going to be first? Thank you.
Thank you, Sam. Brilliant presentation. Sam, so as you mentioned, whenever there is a desert, if it rains, a huge amount of sediment will be washed away, right? However, as you mentioned, it turned into a savanna. So this means more vegetation, and this means this will hold the soil together, which means that when it rains, it will be less sediment. So how do you concile these opposing ideas?
That's a fantastic question. And we call exactly what you said. You have a drought-hardened scenario, that if you have a long period without heavy rain, it hardens the desert. and then when it rains, you get an incredible amount of sediment then starting to move, or you have like a rainfall softened one, which is when you get those savanna-like conditions. So when we make these reproductions of rainfall, we do sensitivity testing into those two end members and then calibrate on whether we're in a drought-hardened type desert or a rainfall softened. So we do take that into account, but it's a very good point. We do that with our computer simulation.
Hi, thank you very much for your talk. I have a question. You said that there's a relation between the sun emission and the rainfall. Have you looked into, I'm pretty sure physics can predict how the sun will be in a couple of years or 100 years. Have you also predicted what the rainfall will look like depending on the sun model?
Well, you can do that, and that's a very good point with the sun model, but the joker in the pack there is the volcanoes. So it's the volcanoes have a huge, and they don't have to be proximal, they don't have to be close, but volcanic eruptions around the Earth and the material they put into the atmosphere, that's the really big unknown. So it's actually quite hard to predict how the sun's going to behave, but it seems at the moment that we're on the uptick of the solar irradiance curve, which you'd think would deliver less rainfall. But the problem now is it's the industrial emissions. They are now replacing volcanoes and starting to scatter light in the high atmosphere. And these are very subtle changes. They're sort of imperceptible in temperature, but seem to have this outlandish effect when it comes to rainfall in Arabia.
Hi, Sam. Martin here. It's good to see you again. I have lots of technical questions. I'll leave those for later. I'm really intrigued by the floods, and I want to share an observation that really fits into this picture. I think last year, it was the last time that I sort of hiked through Wadi Tayyib. You've probably done the same. And if you look at the rock faces to the left and the right, you see that, up in the mountains, it's all rough and, rugged and so on. But 5-6 meters above ground where you hike, the rock surface along the wadi is smooth like a bathtub. So this flood that you showed from 2018 has had occurred, numerous times and even much, much stronger.
Yeah.
So the key question is, what do the NEOM engineers do when they plan their fancy hotels in Wadi Tayyib itself?
Well,
how can you engineer for that? Because you cannot divert it.
Well, that's a very good question, Martin, and I don't have the answer to it. I believe you try and divert it, but the risk, and I think that's what you're alluding to, is if you try to divert a sort of modern level of rainfall, it's entirely unrepresentative of the long-term situation, and you have to think about diverting at least 5 times as much water than we see in the modern era. I do not know how you engineer around it. All I can hope is that the right people are employed on these gigaprojects with that long-term view to make the right engineering decisions, because just like that cyclone in Libya shows that, or even the town planning in Jeddah, that it's very easy to be lured into a sense of tranquility, which is how the climate appears at the moment, but that is deceptive. So I don't have a good answer for your question. It's above my pay grade, but I hope that someone else does.
Any other questions? If not, let's give Sam a very warm thank you for the talk. And we have a thank you gift for you, Sam, for coming and joining us.
Yes.
Okay, for everyone else, that's it for tonight. Thank you everyone for being here, and we'll see you tomorrow. Don't forget to check out and enjoy the food.